Hello, my name is Christina Margarita and I'm a PhD student at the University of Aegean. The subject of my research work is the effect of artificial aging on the corrosion-induced mechanical properties degradation of aeronautical aluminum alloy 2198. Firstly, I will make an introduction to the scientific problem. Later, I will move on to the description of the experimental procedure. Afterwards, I will present with the experimental results and analysis and later with the conclusions. Aluminum alloy 2198 is a newly developed third-generation aluminum copper lithium alloy that was developed in 2005 in order to overcome some disadvantages of the second generation of aluminum copper lithium alloys, such as high anisotropy in the mechanical properties, low shock transfer properties, and crack deviations. Third-generation aluminum copper lithium alloys that contain lower lithium levels offer low density, high elastic modulus, high specific strength, and good corrosion resistance. The main strengthening phases of aluminum-copper lithium alloys are the T1, delta, and S phase. The T1, with a composition of aluminum-2 copper lithium and a hexagonal crystal structure, is more often present after the artificial aging of these alloys, as can be seen in the right figure, and usually on the grain boundaries as well as in the interior of the grains. Aluminum copper lithium alloys are more often used in the fuselage as well as in the upper and lower wing structures of the aircraft, where high elastic modulus, high tensile strength, damage tolerance, as well as high corrosion resistance requirements are needed. According to a research on a Boeing 747, it was found that approximately 40% of the damage problems are due to corrosion. The real degradation of the aircraft structures was found to be a synergy between fatigue damage, natural aging, as well as corrosion damage. However, in the present work, the synergy between aging and corrosion damage is investigated. Among the different accelerated laboratory corrosion tests, the exfoliation corrosion was used in the present work since it is a very aggressive solution and it eliminates the time needed for the experimental procedure. As, according to previous work of the authors, it was found that only 24 hours exposure are needed to have the same elongation fracture degrees with 6 months exposure at naked solution. Moving on to the experimental procedure. Firstly, tensile specimens were machined from the sheets of aluminum alloy 2198 parallel to the rolling direction. Afterwards, the specimens were exposed to artificial aging heat treatment at 170 degrees Celsius. Then the specimens were surface cleaned and exposed to exfoliation corrosion solution. Later, the tensile tests were conducted, and finally the evaluation was done through microstructural analysis and mechanical performance. Moving on to the experimental results and analysis. Regarding the tensile behavior of pre-corroded specimens, a previous work of the authors showed an essential stress drop of the flow curves of aluminum alloy 2024 in T3 condition after only 4 hours of corrosion exposure, shown with the magenta color in the right figure. This degrees was correlated with hydrogen briefment and degrees of the cross-section of the specimens. However, regarding aluminum alloy 2198 in T3 condition, no sudden stress drop of the flow curves is noticed even after the highest exposure time of 48 hours. Elongation fracture of aluminum alloy 2198 specimens continuously decreases with increasing expo time, and a significant strain decrease is noticed after only 2 hours of exposure, shown with the red curve in the left figure. Regarding the corrosion-induced degradation of the tensile properties with increasing exposure time to expo solution of aluminum alloy 2198 in T3 condition, it was found that conventional UV stress, shown with the black curve, remains almost unaffected after being heavily exposed to expo solution, while elongation fracture degrades at higher rates even after the short corrosion exposure times. Regarding the surface morphology of the corroded specimens, it was found that after only 2 hours of corrosion exposure, no surface pitting is evident. However, after 24 hours, the nucleation of pits is evident on the corroded surfaces, and after 48 hours, an excessive surface deterioration with the formation of surface microcracking is evident. Investigation of the corrosion mechanism on tensile specimens of aluminum alloy 2198 through ECM analysis showed that the corrosion problem is higher on the side surface of the tensile cupules. Small pits are evident on the corroded surfaces of the specimens exposed to EXCO solution for 2 hours, while a higher corroded area with more pits is evident after 6 hours. However, after 24 hours of corrosion exposure time, a larger corroded area with several micro cracks is evident. The significance of the side surfaces to corrosion-induced degradation was investigated through a comparison of the tensile mechanical properties between the specimens covered in its side surfaces and the specimens non-covered. No essential change in conventional yield stress shown with the black curves was noticed between the non-covered and covered specimens. However, the covered specimens exhibited high corrosion resistance. A notable change in elongation fracture between the non-covered and covered specimens was noticed that increases with increasing exposure time. These results are in accordance with the previous work of the authors, where accumulated corrosion on the side surfaces was found to play a pivotal role on the elongation refractive degrees of aluminum alloy 2198 in T351 condition. The effect of corrosion on artificially aged specimens of aluminum alloy 2024 was investigated in the previous work of the authors. Specimens exposed to 2 hours corrosion exposure time and in 3 different artificial aging temperatures. It was found that the lower corrosion-induced degradation of elongation fracture was evident in the peak aging condition for the 3 different temperatures. However, this degradation increases with increasing the artificial aging temperature, where from almost 11% at 170 degrees Celsius, it was increased to almost 18% at 210 degrees Celsius. As was shown in the previous slide, the lower corrosion-induced degradation of elongation fracture was evident in the peak aging regime of aluminum alloy 2024, where degradation due to EXCO exposure in peak aging decreases from 26% to almost 11%. However, for the case of aluminum alloy 2198, the degradation stays almost stable. However, slightly lower corrosion-induced degradation is noticed for the under-aging condition in this alloy, and elongation fracture in peak aging and over-aging stays almost stable. The results of the potential dynamic electrochemical measurements showed that the under-aging condition has almost the same corrosion potential with the T3, but lower cathodic activity. And the T8 and peak aging conditions exhibited an essential increased shift to more noble values of the corrosion potential. Regarding the comparison of tensile behavior in T3 condition of aluminum alloy 2198 shown in the left figure and the T8 condition shown in the right figure, it was found that higher degrees in axial nominal strain is noticed for the specimens in T3 temper, while no significant stress drop is evident for the T3 condition. Higher yield stress values are noticed for the T8 specimens due to artificial aging, but a sudden stress drop is noticed after only 6 hours of corrosion exposure time. Regarding the corrosion-induced degradation of the tensile mechanical properties in T3 and T8 condition, it was found that the unconventional yield stress of the alloy in T3 temper seems to be unaffected by corrosion exposure time. Regarding the T8 condition, a remarkable conventional yield stress degrees is noticed, especially for the short exposure times and up to 6 hours. For the highest exposure time, almost the same degradation percentage was noticed for both tempers. Regarding elongation fracture, the elongation fracture is decreasing with higher rate in T3 condition than in T8 and up to 12 hours of corrosion exposure. Elongation fracture of 2198 in T3 condition is reduced by approximately 37% after 24 hours corrosion exposure time. The respective reduction for the T8 temper is almost 15%. Significant differences are also evident for the typical fracture surfaces after corrosion exposure times between the T3 condition and T8 condition of aluminum alloy 2198. For instance, for the T3 condition, a localized corrosion morphology is evident, while for the T8 condition, the corrosion morphology seems to be more uniformly distributed to the whole surface, probably due to the distribution of the precipitates. Additionally, no significant difference between the different corrosion exposure times is evident in the T8 condition, while in the T3 condition, the differences in the corrosion morphology between the different corrosion exposure times is evident. The main concluding remarks of the present work are that lower degradation of elongation and fracture due to corrosion exposure is noticed in the packaging regime for aluminum alloy 2024, while for the case of aluminum alloy 2198, the lower degradation of elongation and fracture due to corrosion exposure is noticed in the under-aging condition. T8 and peak casing tempers of aluminum alloy 2198 are less susceptible to corrosion attack, while specimens in under-aging temper corrode in lower rates. The alloy in T8 condition is more corrosion resistant regarding the elongation and fracture degrees, and especially in the short corrosion exposure times up to 6 hours. Surface corrosion attack in the T3 condition seems to be localized, while in the T8 condition is uniform in the whole surface. Such surface attack play an important role in the elongation and fracture degrees for aluminum alloy 2198. Thank you very much for your attention.